By way of background, I have been a professional tutor in the calculus physical sciences tutoring lab for about 4 years, and I was a volunteer tutor for maybe 6, 7 years before that. Before that, I taught the only class at GVSU that was entirely devoted to relativity. So I've had a lot of interest in the topic, obviously, for a long time. But it always frustrated me when I was teaching at Grand Valley that it was an open enrollment class. So it wasn't limited to math majors or physics majors. Anybody in the university could apply, which sort of restricted the mathematical depth into which you could go. And so I'd give them a small taste of special relativity in the form of the Lorentz equations, and that made a lot of eyes roll back in heads. But I never got close to the real mathematics involved in general relativity. I hope everybody's had a chance to pick up a copy of the free handout. I guess if you say handout, it's got to be free. But anyway, I am not necessarily going to cover all the stuff in the handout. It's a little more formal presentation of a lot of the topics than the casual approach I tend to take when I'm speaking, but I will also be talking about some things that probably aren't covered very well in the handout simply because I ran out of time. Please hold your questions until the end. We have an awful lot of ground to cover in a limited period of time, unless I make an obvious and correctable mistake, in which case I'd appreciate your jumping in and pointing that out to me. One at a time, please. I mean, just not a pile on, because usually the mistakes I make are like whoppers, and everybody just okay, without further ado, I want to tell you about a trip that I recently took to Space Station Hadley, which is, as the board indicates, 300,000 kilometers away from the great city on the hill, GRCC, safely back at home. And I happen to be traveling in my own personal rocket ship. And I leave the rocket ship leave GRCC in my rocket ship at precisely the same instant that a light signal is sent, as light signals are regularly sent from GRCC to Space Station Hadley, just to see how they're doing up there. And occasionally they also get messages back, but those are less frequent because rumor has it that Space Station Hadley is a very, very fun place to be. So I leave at the precise instant that signal is sent from GRCC. That's at time 0.0 GRCC local time, and in relativity that has consequences. And as everybody in my tutoring lab knows, I am able to instantly accelerate to any speed that I want to, short of the speed of light, because I carry around on a regular basis a shielded black hole in my pocket. Now, some people have Swiss Army knives in their pocket, and that's okay, but let me tell you, a shielded black hole is a lot more useful than a Swiss Army knife, particularly if you want to get somewhere in a hurry. So instantaneously, as far as anybody can figure out, as soon as I leave GRCC, I am traveling at 0.9999 times the speed of light, which, as you all know, is 300,000 kilometers per second, or 3 times 10 to the 8 meters per second. And I'm going on my merry way and watching this signal as it moves away from me, because obviously I'm going slower than the light signal, and eventually I record it in my reference frame, arriving at Space Station Hadley. The question is, at what time on my watch does it arrive? And I need to go into all of this because this is special relativity. But some of the things that are essential to an understanding of the mathematics of general relativity have to be covered at this point, just so you know what, for example, some of the sign conventions mean. Well, in 1905, Einstein published his theory of special relativity. It raised quite a sensation at the time. Frankly, it blew everybody's mind. He didn't even win a Nobel Prize for it. He got his Nobel Prize for his contribution to the understanding of the photoelectric effect. And as far as I know, he never won a Nobel Prize for any of his work in relativity. Why? I don't really know. I suspect it had something to do with politics and the fact that, people just didn't want to believe some of the stuff that his theory was predicting. So anyway, Einstein came to the realization, or was actually the first one to take seriously the notion that the speed of light is the same as measured in all inertial reference frames. Now, what does that mean? If you are driving down the highway, going 60 miles an hour, pretty slow on today's highways, but let's say you're going 60 miles an hour, and you are passed by a student trying to get back to Michigan or Michigan State at 90 miles an hour, you see them go by you at the difference in the two rates. With respect to you, they are passing you at 30 miles an hour, right? Okay. If you are moving, as I was recently, at 0.999 times the speed of light, and I leave at the same instant as the light signal from GRCC, it's moving away from me at 100% of the speed of light. The question is, how fast does that light signal appear to be going to me? Well, if you're Galileo and everybody up and before 1905, well, that's pretty obvious. You subtract your speed from the light speed, and the difference must be the speed of light relative to you. No. I don't want to go into the Michelson-Morley experiment. We don't really have time for all of that. But I don't think Einstein was probably even aware of the Michelson-Morley experiment when he came up with this astounding, his ideas. Actually, he started with Maxwell's equations. And Maxwell's equations predict that the electromagnetic waves, all of them, will move at the same speed regardless of their frame of reference. So Einstein took this literally and said, okay, if that's true, then if I'm moving relative to somebody else's frame and they measure the speed of a light signal based on how far that light signal travels in a given period of time, and then how long it took to get there, they'll come up with 3 × 10⁸ meters per second. If I'm moving very, very fast relative to them, and I measure the same interval, and we'll get to the meaning of that in a minute, but if I measure the same interval, in this case between the signal leaving GRCC and it arriving at Space Station Hadley, that is, I measure the distance from between GRCC and Space Station Hadley, but in my reference frame, and then divide by the time, I've got something's wrong here. Obviously, we're not talking about the same distance and the same time. For starters, what in the frame of reference of GRCC is a distance of 300,000 kilometers away, which takes 1 second for that light signal to cover, and I'm going this fast and you can do the math, non-relativistically, you can figure out that at that rate, I'm only going to be 3 kilometers away from Space Station Hadley at the end of that period. So in my frame, remember I started out here. So I was here at the beginning of my journey, and I ended up 3 kilometers away from there. So in my frame, I covered the difference. 9,000, however you want, all the difference between 300,000 kilometers and 3,997 kilometers. And yet I'm going to measure the speed of light to be 3 times 10 to the 8th meters per second. So if my distance is that much shorter, and I get the same result when I divide my distance by my time, I guess it didn't take me a full second to get there. And that's right. The question is, what are the changes? Well, that's answered by the Lorentz transformations, which are based on the notion that if you are traveling very, very fast relative to another observer, that other observer at rest is going to watch. If he can see your watch, it will appear to be running much slower than his. Not to you. Your watch is running at the same rate. You don't notice any change at all. It's perfectly normal. But your watch is going to be appearing in his frame to be running much more slowly. So in his frame, it took you that long. In your frame, it's more like 0.002 seconds that it took you. And to offset that, it means that the time the distance that you traveled in your frame is much, much less. Not only because you covered so much distance in the meantime, that's part of it, but also because as he looks at it, your distance has been compressed down to nothing. Or, I always get confused at this point. And so you actually, on your watch, arrive at Space Station Hadley a fraction of a second, a small fraction of a second later, but you've only covered a correspondingly very, very small distance. Now, this is all spelled out in the Lorentz equations, and I can't remember if I put them down. You can look them up. And basically, the Lorentz equations, with some fine tuning, are basically the entire mathematics of special relativity. So, upshot is that from the Lorentz equations in special relativity, the concepts are very hard to wrap your head around at first. I only scratched the surface. There are all kinds of paradoxes that are set up in special relativity, and particularly in first-year classes. We teachers love to dwell upon them. Like if you are running with a ladder that's too long for the barn that you intend to store it in, how fast do you have to run to make the ladder which will be shortened, fit in the barn, but what happens when you put it down? That's one of them. The other one, probably more famous, is the twin paradox, and I love the twin paradox, but it's important to the rest of our story, so I get to tell the story. In the twin paradox, my twin stays at GRCC, and I make the trip to Space Station Hadley and back. And you'd think from the symmetry of the situation, you know, I see, my twin sees me go 300,000 miles, it takes 1 second, and then turn around again with my pocket black hole, turn around and zip back, and 2 full seconds has elapsed. But no, on my watch, 0.22 seconds has elapsed. But wait a minute, isn't it the same if I'm watching my lazy, stationary, lazy isn't a good word, stationary cousin just sitting at GRCC, they appear to be going backwards at the same rate I'm going forwards. And they appear to turn around and come back towards me. So what's happening here? Are we both the same age? Is somebody older, somebody younger? Turns out, and again, this is important for understanding general relativity as well, that the observer who is accelerated at some point during this mission definitely will have less elapsed time on their watch and will age less than the stationary observer. And it's not just that, you know, they feel a little better. They're literally less time has passed for them if they've gone out, started, sped up, stopped, turn around, and come back simply due to the acceleration. All right. A lot of this can be illustrated with what we call space-time diagrams. And again, I got to keep an eye on the clock. But basically, when you're dealing with reference frames, you have to be very, very careful about whose frame you're working in. And the space-time diagrams are a good way to illustrate that. This is the Grand Rapids Community College frame. Space-time diagram has the distance, any distance, be on the horizontal axis and time on the vertical axis. But to keep the units consistent, we always multiply the time interval by the speed of light, turning what are meters down here into meters up there. And in any space-time diagram, like any other graph, you need to have an origin, which is identified with an event. Now, in relativity, we deal almost always with just events. Because space in and of itself, time in and of itself, don't have any inherent meaning. It all depends on what reference frame you're in. So if we're moving very fast relative to each other, my time is a mixture of your space and time, and vice versa. But there are invariant quantities, again, which are very important. We'll get into those in a minute, but let me just show you what's going on here. So this is the GRCC frame. In the GRCC frame, GRCC is at rest. And if you're at rest, obviously you're going nowhere in space, but you're always moving ahead in time. So GRCC starts at the origin because that's where we choose to put our origin in the GRCC frame. and is moving in the time dimension at a rate of the speed of light multiplied by the time recorded on somebody's watch who's parked at GRCC. I use the Latin T because that's normally used for I shouldn't say it, not proper time. I'll get into proper time in a minute. So going back to this world line, some other things to explain. As long as you set up your axes like this, you can then draw two 45-degree dashed lines, and those represent the boundaries of what we call the light cone. And the light cone is divided into two regions. There is the time-like region, which is in this quadrant and this quadrant, and then the space-like regions to the sides. And we call them space-like because no action taken at the origin can affect anything, any event that occurs in the space-like quadrants. Why? Because a light signal, the fastest thing there is, speed of light, as far as we know, nothing can go faster, always travels along, light signals always travel along the 45-degree line. So the best you can do to make something happen somewhere else is send a light signal to notify people that you want something to happen there. If you can't do that, then you can't affect anything that happens in the space-like regions. Conversely, things that are in the time-like regions can be reached by some kind of a signal. In fact, you can even reach them yourself if you just sit tight and go along with the flow of time. So that's what that's all about. And then we can draw what amount to velocity vectors based on the relationship of any moving object with respect to the speed of light. Now, this is not necessarily drawn to scale, but I've drawn, first of all, I've drawn obviously the GRCC, we call it world line. I've drawn the light signals world line, and then I've drawn two other world lines. One is my world line, which is close to, but not quite at a 45-degree angle. So I'm moving in the time-like region, which I have to. And then the other world line is the world line of Space Station Hadley, which begins 300,000 kilometers away, but it's at rest with respect to GRCC. So in this reference frame, its world line also runs straight up. Now, a collision, obviously, is when you are in the same place at the same time. And so you can mark the collisions, two collisions in this case, by finding where world lines intersect. And I forgot to mention this earlier. We can pull this little trick with reducing all this three-dimensional space to one dimension, because as it turns out, the action only happens, the real action in special relativity, only takes place along the axis in which you're moving. There is no effect, and the Lorentz equations reflect this, on the other spatial dimensions. It's only the direction in which you're moving where distances are shortened. So we always assume that you're moving in the x direction. You can call it anything you want. So anyway, two collisions. The light signal, which travels fastest, reaches the world line of the Space Station Hadley. first before I get there, and because it's exactly one ice station is, of course, was put there precisely because it's 1 light second away from GRCC. Keeps the math easy. So exactly 1 second in the GRCC later, the folks at GRCC, because they got good math skills, realized that their signal must have arrived at Space Station Hadley, and then because I'm moving a little bit slower, they record my arrival there a fraction of a second later. But that's in their reference frame. So the situation looks very different, though, from my point of view. In my point of view, of course, I'm at the origin, and in my reference frame, namely the spaceship, I'm not moving relative to the spaceship. I'm just minding my old business, poking along, and so my world line in my reference frame is straight up. After my initial bump and go, I have no sensation of any forces acting on me. If I look out the window, things go, but it's nice viewing, but I don't feel anything pushing or pulling me. So mine is straight up. But again, because of the invariance of the speed of light in all reference frames, I still can draw, or have to draw, the 45-degree lines for all light signals that originate at my origin. But remember, my origin coincided with the GRCC origin at the start of my journey. So this represents, at that point in time, the same location as the origin over here, but things rapidly change after that. Now, because as I see it, the space station is coming towards me. That's all when I look out my front window and there's the space station coming quickly towards me, I see it doing this, and eventually we collide. That is, I arrive at the space station in this period of time. But this period of time, and again, we don't have time to do all the Lorentz equations, I wish we did, is not 1 second. It's a very small fraction of a second, and this distance is a very small fraction of the reference frame, the distance in the reference frame, which is 1 light second. And then because the GRCC world line has to be parallel to the space station world line, because they are moving together in my reference frame, they must maintain the same distance, a consistent difference in any reference frame as long as they're not moving with respect to each other. So without further ado, invariant intervals. The important thing to come out of all of this is that even though in different reference frames, your space is a mixture of my space and time and vice versa, between any two events, there is what we call the invariant interval. And you can work it out from the Lorentz equations, but it goes like this. The invariant interval, which I'm just going to call I, some people want to say I squared, but I just call it I, is equal to the minus the difference in time between the two events squared plus the difference in the spatial location, that quantity also squared. This will be the same in every inertial reference frame once they've done the math. And this right here is what gives both special and general relativity let's say it's spice, because space-time is not Cartesian. You don't add the squares up and take the square root to get the difference. If you want to get the distance in space-time, the difference in space-time, you add up the squares of the distance, spatial distance measurements, and then you subtract the square of the time difference. And as long as we're not working in geometrized units, and I won't bore you with what that means, this really should be delta CT quantity squared to keep the units consistent. So since once you throw in this, you can see that, you know, it can make a whopping big difference. And again, the formalism here is the same as I described before. If this quantity I is negative, you have a time-like distance, or time-like interval, meaning that a light signal could have passed back and forth between the two events. If this is positive, then the space portion dominates and you have a space-like interval between the two events, and nothing that happens in one event can affect the other event. Now, this gives rise to what we call in the trade a four-vector. And a four-vector is simply what you'd expect, the vector that you make out of the four dimensions of space-time. All right? So normally, and the conventions, it all varies, of course, but normally, I think because most of us would rather deal with fewer negative signs, particularly those of us whose, how shall I put this politely, whose arithmetic skills are challenged, and the fewer negative signs we have to deal with, the happier we are, the fewer errors we make. So because there's only one of these and three of these, this tends to get the negative sign for that reason. It could be just the other way around. The sign assignment is pretty arbitrary, except that these all have to be of the same sign. And normally we put the negative sign on the time component. So a four vector typically will have a time component, and in the trade we usually like to keep things general, so frequently it just simply goes as XO, and then we have an X component, which is frequently just X1, X2, X3, and so forth with the time. Normally, there's some authors put the time last and call it the fourth component rather than the zeroth component, so conventions vary. Now, why isn't there a negative sign out in front of this? Well, because we've got a square up here, okay? And some people say, well, we'll just make this, in order to get the square up here, we'll just make this IC. So when I square that, I get the negative sign. But that doesn't work very well. So it turns out that the only effective way to deal with this, this feature of 4 vectors, is to introduce covariant and contravariant components of various vectors. Now, it's in the handout. Contravariant and covariant components transform into other reference frames in different ways. And it has to do with the operation of the chain rule. It's in the problem. But think, when you're thinking covariant, think gradient. When you're thinking regular vectors, which is most other things, think contravariant. And as I've noted in the handout, there's a whole different way that the term covariance is used, has been used since the time of Einstein, and that is to identify features of the theory that are not coordinate dependent and can be broadly stated as the laws of physics must be the same in all, not only inertial reference frames, but once you get into general relativity, all reference frames, regardless of whether they're inertial or not, whether they're accelerated or not, or whether they're subject to gravity or not. So this terminology, notation, it means contravariant indices. When you drop them down to the bottom, they become covariant indices. So how do we handle exponents? Like that. So, and this can drive you crazy. You get some of these books. Look at my favorite here. And this is cited in the recommended reading at the end of the handout. But there are literally 10,000 equations in this book. And they all have this notation, and you've got to sit there and puzzle over it and just say, I'm going to be good, Mike. You say, what the heck does this mean? All right. So, how are we doing for time? Let's go so fast. So, invariant interval, we covered that. There are other invariant quantities in relativity that are built from 4 vectors. One is the momentum energy 4 vector, in which the zeroth component is energy or energy density. So it's energy, I'm just going to call this as XO, energy, and then the other components, the spatial, this is the time component of this particular 4 vector. The other components are momentum. Good old, well, it's not good old momentum, it's relativistic momentum, which involves a whole lot of applications of the Lorentz transformations. But basically, this vector has energy and then 3 momentum pieces. And this can be the energy of a particle, the total energy of a particle, including its rest mass, or it can be an energy density. And when we get into, hopefully, get to the Schwarzschild metric, it's all about mass density once you're inside a star, but we probably won't even get there, so why bother? So the invariant quantity that's formed out of mass and energy goes like this. The rest mass of an object, and I'm going to skip all the c squareds, and well, I'll do the c squareds. M naught c squared. The rest mass is equal to E squared minus the sum of the vector sum of the momentum vectors squared. This is an invariant, and it makes sense because if you have no momentum, nothing's moving. All you've got in form of energy is the concentrated energy stored up in this mass. Once it starts to move, this goes up and this goes up, but this quantity remains the same. Rest mass, as far as we know, would be measured the same throughout the universe. By definition, a rest mass isn't moving. Once you set it in motion, then things change, but the rest mass, just sitting there, a lump of whatever, that's always going to be the same, and that's very important, especially in general relativity. All right. All right. Yeah, talk about the hyperbolic nature. That's just the c squared minus the t squared minus e squared. Finally, with a whopping 15 minutes to go, we come to general relativity. As far as we know, there are 4 fundamental forces in the universe: the strong and weak nuclear forces, very powerful, very short range, don't affect our daily lives. And then the only other 2, as far as we know, everybody's always claiming to have done an experiment that proves that there's, something's happened that isn't explainable and by any one of the 4 known forces, and later on they find out, maybe they busted the experiment, maybe they didn't think about their results, and it always goes back to the original 4. The other 2 are the electromagnetic force and the force of gravity. That's it. And those 2 forces are all the forces that account for everything we see in our day-to-day lives. So obviously, general relativity is all about gravity. And gravity is different from the other forces. Gravity is, first of all, it has a vastly further reach than any of the other forces. It's very weak. Just look at the universal gravitational constant to see that it's very weak, but it only acts in one direction. And so it's the accumulation of all of those attractive forces, particularly when you're dealing with huge masses, that account for its reach and its power. Gravity is basically what holds or doesn't hold the universe together, and since 1998, we're not really sure that it's ever going to stop expanding, but that's for another lecture. Gravity is unique in another way. Gravity is, unlike the electromagnetic force, doesn't make you feel like you're being accelerated. In fact, Einstein is famous for saying that the happiest moment of his life when he realized that, if he was in free fall, if anybody is in free fall, they will have absolutely no sensation of being accelerated because they experience no push or pull. Now, you'll say, yeah, but something's happening out there. What holds me on the ground? Isn't there a force? Newton says there's a force between me, you, and the earth, and we pull each other together, and that's what keeps the whole thing going. Einstein says, no. Gravity is not a push or a pull. Gravity is the curvature of space-time by mass. That's one half of it. Mass tells space-time how to bend. Space-time tells mass how to move. And that blows people's minds. But suffice it to say that Einstein is right, if only because his theory explains a lot of things that Newton's law of gravity does not. Not only the sensation of feeling any force acting upon you when you're in free fall, even though with respect to the ground you're accelerating, but also the fact that gravity bends light. Light has no mass. Newton's law of gravitation holds that the force is equal to the universal gravitational constant multiplied by the product of the masses and divided by the square of the distance between their centers of mass. So, according to Newton, if you have something with no mass and light has no mass, there wouldn't be a force at all. But it's been proven over and over again that when light grazes a large object, a star, it bends. Its trajectory bends just like everything else. It doesn't bend as fast, but that's because it's going so fast, but it still bends, and that is not predicted by Newton's law. There are some other things. The perihelion of Mercury was one of the early experimental confirmations. No one had been able to figure out the strangeness of the orbit of Mercury, and Einstein's first achievement was to take this oddity in the orbit of Mercury, which had long been observed but could not be explained on the basis of Newton, and showed that using his rules that everything turned out to predict the exact orbit. All right. And I do a little song and dance about the hammer falling on my foot and it hurts, and I blame gravity because if I hadn't dropped it, and you blame me because I was stupid to drop it in the first place. But the simple fact is that the hammer is not to blame. The only acceleration in Einstein's view that's going on here is that the floor that I'm standing on, what we call the normal force, is exerting a force upwards, which is all electromagnetic, as it turns out, exerting a force upwards that deflects me from what would otherwise be my geodesic shortest possible path through space-time. So it's not that the hammer is falling on my foot. The hammer is just resting where in its position. It's that the normal force is deflecting me away from the path that I would otherwise rate at exactly the acceleration due to gravity at the Earth's surface. Now, finally, I get to the punchline. All right, so Einstein struggled with this for years, and he had all of these ideas about free-floating objects and space, or gravity is really space-time curvature, but it took him a long time to work out the math because it is hideous. And exhibit number 1. There's a lot of good stuff in here that's not, but it's all math, and it is really, really difficult math. It all involves tensors. What is a tensor? Just to get a show of hand, how many of you know what a tensor is? How many of you are comfortable working with tensors? I'm still not after a long, long time, but a tensor is just a generalization of vectors because there are physical things that we want to examine that have direction laid on direction. You cannot represent them with a single object that has a single direction and a single magnitude. You have to have, you take that for a starting place, but then, and the most obvious case is a tangent vector. In Calc 3, we learn about tangent vectors, and you learn that as a tangent vector moves along its curve, its direction changes as it moves. So you have the direction of the tangent vector, but once you differentiate its how it changed it to find out how it changes as it moves along its path, you then have a different vector or set of vectors that describe how it changes. And in general, every time you take a vector and differentiate it to see how it changes, and then differentiate that again to see how it accelerates and so forth and so on, every time you go through that process, you're creating a higher order tensor. And they can get fairly hairy. Fortunately, most of the stuff that matters can be done with a second order tensor, a zeroth order tensor being simply a scalar. First order tensor is a vector. Second order tensor can be represented by a square matrix where the components, you have as many components as you have dimensions in the space that you're working with. So in general relativity, our tensors tend to be 4 by 4s. Einstein's tensor, which I hope to get up on the board before we break up here, is a 4 by 4 symmetric tensor, which makes it manageable because a 4 by 4 tensor has potentially 16 different components, but you make it symmetric, you cut that down to 10. If you make it anti-symmetric, you cut it down to 6. So you say, easy peasy. You know, I only have to work with 6 components here, or 10 components. I don't have to, work with 16 components. Well, I wish it were that easy, and to show you not, I'm gonna, first of all, make one passing note. Every time you differentiate a tensor in a non-linear, non-Cartesian, non-Euclidean space, you don't just change just the components, you change the basis as well. And to deal with that, we have in the trade what are called connection coefficients, also called Christoffel symbols, which are represented by a capital gamma, and they play a major part in the calculation of the ingredients that go into the Einstein tensor. Now, I'm going to write down Einstein's full field equation in one of its many forms. On the top of page 1, you can see it in Einstein's original form, where he writes the G subscript mu subscript nu is the Einstein tensor, and that is equal to how did that negative get in there? Well, probably came from a good place. Oh, Albert Einstein said it's a negative sign there. Okay, so and where K is Einstein's gravitational constant. It's a combination of the universal gravitational constant and a couple of other things that we won't go into. And then that's multiplied by T, the stress energy tensor, which is better described as the momentum energy tensor. It is the tensor version of the energy momentum vector that I wrote down before. But it's more complicated than that, and so I'm going to write down another version, and then I'll probably have to stop there without getting to Schwarzschild, but okay. So G, the Einstein tensor, mu nu plus, we never got to the metric. Mu nu equals, and this is what goes into the K, 8 pi gravitational universal gravitational constant, not to be confused with this G, which is the Einstein tensor, over C to the 4th power, and then that's multiplied by the energy momentum tensor. The problem is that you can't figure this out until you figure out the metric. And you can't figure anything out until you figure out this, but you can't figure out this until you have the metric. So it becomes a question of where do you start? And the answer is it's hard to start any place. There are very, very few perfect closed solutions to the Einstein field equation. And for the sake of at least getting it out, this is critical. This is what we call the metric tensor. And it describes an infinitesimal displacement in 4-dimensional space-time. In other words, local curvature. And you can do all kinds of wonderful things with it. This is what you use to raise and lower indices so that you can contract nasty tensors into nicer tensors, for starters. But the problem in all of this is that it's all interdependent, and these are non-linear differential equations because there's nothing is fixed. And one of the main theses of general relativity is that we know we live in a curved four-dimensional space-time. But as far as we know, there is no Cartesian higher hyperspace. In other words, we can't solve our problems by imagining yet another space in which we're all embedded, but we could take straight measurements in the hyperspace. It may be out there, but we can only investigate the space that we live in with the tool we have. And to use a crude analogy or an analogy, I don't know how many of you are familiar with flatland. These flat creatures who live in 2 dimensions, but they know the 2-dimensional surface they live on is curved. When they start doing geometry, and they'll take a trip around in a big circle, and they'll find out that the circular path they just walked is less than pi times the straight distance when they go straight through the middle of the circle. Therefore, they've got to live in a straight. Well, our situation is analogous to that, except we live in 4 dimensions. And we have ways of investigating the curvature, but none of them involve, making things right by imagining there's yet another hyperspace in which we live where everything is straight. So with that, I will end and ask if anybody's got any easy questions. Okay?
All right, thank you very much. Thank you.
Once you decided you didn't want to be a lawyer, why did you decide to go into teaching?
Right.
It's because I got lucky. I mean, I had a wonderful physics teacher in high school back when the Los Angeles public schools really were the best public schools or best secondary schools for that matter in the country, or some of the best. And so I had a great physics teacher, and then I lost my way in college and went into the liberal arts. Ended up with with an economics degree, which I guess is not too liberal artsy, but it was still an AB. And as you know, I went in the Army, and that was the hardest but most educational experience I almost never had. And then I came out and I said, well, my daddy wanted me to be a lawyer, so I became a lawyer. So after I got all that out of the way at the age of 45, I said, I want to be a teacher. And I said to myself, what kind of a teacher? And first I thought about being a Latin teacher. Good thing I didn't get that. And then I said, well, if I really could choose what would I want to teach, I'd want to teach physics in high school. And one thing led to another, and here I am in the world's best gig.
To me, it was always an interesting story because in midlife, you decided you wanted to teach physics, and I don't think there are too many people who do that. So that's fantastic.
Well,
and it is true.
Well, the simple answer is that I'm crazy, but everybody knows that. So.
A little bit. I guess also it is Veterans Day, and you have before you not only a veteran but a medal-winning veteran, Bronze Star.
Shucks.
So thank you. Thank you very much.
Have you read the book, Mr. Tompkins, in paperback?
I have not.
Oh, really?
No.
Oh, it talks about time compression, and it puts it in a really neat perspective of travel. I have it if you'd like to borrow it.
That'd be fine. Now I may actually have some time to read. I mean, this is one of the things I love about teaching is that you don't really understand a subject until you have to teach it. And so I have just working my tail off for the last several weeks, just trying to wrap my head around this stuff. And I've been doing this for over 20 years now, trying to figure this stuff out. And I mean, as recently as, you know, an hour before I came down there, I was still trying to figure out, okay, what if we get to metric tensors? How do I explain what you do with a metric tensor? And there's something about, you know, you take two vectors and you put them into the slots and you turn the wheel and it spits out a number, which is the way Wheeler and Thorne and Meisner tend to write things. You know, you got this machine and you put two slots in, and I said, I don't understand what that means. So when he asked me that question, I'm not going to be able to answer it. So thank you. I would like to.